This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Today's speaker, Professor Vivek Sharma, who is also in UCSD's Department of Physics, is one of our university success stories. He's one of the leaders in searching for the Higgs boson. That's what he's going to tell you about today. He was recruited as a professor of physics to UCSD by former chair of physics Roger Dash in 1995. In 1999 to 2005, Vivek's group at UCSD has played a leading role in the discovery of antimatter asymmetry and the decay of mesons made of beauty quarks. This experiment was sort of beyond important because there had been a theory some 30 years previously by a Japanese group that this should happen, and it was his work and that confirmed this, and the Japanese group that predicted this won the Nobel Prize for this work. As a postdoc at the University of Wisconsin, he already, in the very beginning, was working on subatomic physics and was responsible with a group for the discovery of two subatomic particles made of the beauty quark. So, without further ado, my colleague Vivek.
Thank you, Mark, for this very kind introduction. Good afternoon, everybody. Thanks for coming. It's a pleasure to be here and to share with you a story which is which began last year. It has been in preparation for several years, but it really began last year and will culminate in the next 2 years into what we hope is something significant. So I'm going to tell you a story, and I'm going to show you a lot of pictures, but first I want to motivate what this is all about. So as of March last year, 2010, the Large Hadron Collider roared into action, and this led to essentially birth of a new era in fundamental science. As you will see, this is the largest scientific enterprise ever, and it's a machine built by the world, by citizens of this world. No one particular country dominates this, for discoveries in particle physics, which is the science of the very small and the very large. This is the timeline of the universe since Big Bang. The universe is about 13.7 billion years old. We are here. And the machine that I'm going to talk about is going to investigate the time domain very soon after the creation of the Big Bang. Less than a billionth, closer to the trillionth of a second since the universe was formed. So in that sense, it is something that I always wanted. A time machine, okay? The LHC addresses what is essentially civilization's curiosity for simplicity in the nature around us. I mean, the philosophers, they didn't do experiments, but they had some thoughts about what nature was all about, what its simple elements were. Fire, air, water, earth, were some of the common concepts. Things improved a lot when experiments got involved, and this is the classical science, and the periodic table is one of the grand synthesis of scientific experimentation and thought. At that point, we understood nature to be made up of something like 100 basic elements. This is what nature was made up of. Then, at the turn of the 20th century, when experiments got even more sophisticated and quantum mechanics came about, the atom was penetrated by alpha particles. And now, back then, we learned that there are two basic elements, not 110, and this is the electron and the nucleus. So this is early 20th century. Today, we have this is our modern view of nature's ingredients. Matter is made up of molecules, which are made up of atoms, which look like this. They have a nucleus with electrons somewhere around them. Then if you peer into the nucleus, as people have by smashing particles through it, you see that the nucleus is made up of protons and neutrons. And then if you peer into the proton, you find that it is made of these whimsically named particles called quarks. If you want to remove an electron from an atom, you need about 14 volts. So about 10 of these batteries will do. So that's the force of attraction between them that puts them together. But if you want to remove a proton from a nucleus, you need 10 million of these guys. That tells you the strength of that force which binds things inside the nucleus. And so there are different forces, two of which are already familiar with you. One is electricity and magnetism, electromagnetism, and the other is gravitation. And so today, what we know of nature's ingredients in terms of forces are these strong interactions which keeps the quarks bound together into protons and neutrons. Electromagnetic waves, which if you carry a cell phone, you sense it all the time, or use it all the time. Gravity, you can never forget, and weak interaction, which is what causes the sun to burn. And it is also the source of radioactivity. So this is the modern view of what nature is made up of. Question is this it? Is quark really the elementary particle, or is it made up of something else, just the way a proton was? Some time ago, people thought protons were elementary. Turned out it's not so. So is this all, and how would we know? This is where LHC comes in. This is the next step forward. It's the world's most powerful apparatus, but it answers and probes the same two basic questions that people have for a very long time. What are the very elementary constituents of matter, and what are the forces which interact with them or which control their behavior? We can learn these things because LHC will allow us to recreate fundamental particles and their interactions that existed very soon after the Big Bang. Okay? So we will basically make little universes to understand what the answers to these questions are. Now, there are questions concerning the universe which are interesting. What was the universe just after Big Bang? Are there undiscovered force fields of nature? Is the universe supersymmetric? What is the nature of dark matter? Are there warped extra dimensions of space? And what happened to antimatter in the universe? And answers to all these questions, not answers, but probing these questions is the purpose of LHC, which is actually a general purpose facility. It's not just a machine, it's a machine which people asking different questions come to collect data and understand, or come to the answers that they seek. This is the UCSD group. The UCSD group has a very high profile role in the CMS experiment, which is at the LHC. It has 4 faculty members, Jim Branson, who is sitting over here, Frank Werthwein, and Avi Yagil. This is a set of post-PhD researchers, graduate students, and the most important, the undergraduates. Okay? These guys have their own missions. They have their own questions of what they want LHC to answer to them. And I hope that one day they will get a chance, based on their discovery, to be in a situation like this and tell you what their journey was and what they discovered. But what I'm going to do today is talk about just one thing, which is the central mission of the LHC. And that is to explore the mystery of the letter M. And M is the letter which gives the universe its substance. I wanted to put a Dr. Seuss M here, but because this would be a... But it's all about M, as in mass, okay? So that's the question. People have observed on mass of matter before. Newton was, well, which equation is this? Which of the laws of Newton? is this, F equals ma. This is what Newton wrote of this letter m. The quantity of matter is the measure of the same arising from its density and bulk conjointly. I could never write things like that, and I don't understand much. But what he's trying to do is an object has a property called mass, and if you apply a force on it, then depending on its mass, it kind of accelerates a little bit or not. Einstein later, this is a famous equation which needs no introduction. It just tells you energy and mass are equivalent, and this is the exchange currency, c, the speed of light. Massless particles travel at the speed of light. Okay? Light is, photons are massless. Massive particles travel slower, and another very important thing that I won't comment on, which is that mass curves space-time. So mass, 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 everywhere mass. Now Newton's definition of mass, this very poetic description, this was good enough for scientists for 200 years, because scientists, first they want to know, how mass works. And then you want to know why it works. Now, we're pretty convinced that F equals ma works. We're not going to investigate that, but the why of the mass is now an intense topic of research. An understanding of this origin of mass is what will be needed to either complete or to extend what we call standard model, which is the synthesis of our knowledge of elementary particles and interactions and nature, as it were. So again, to remind you, in size in atoms, this is an atom. It's made up of a nucleus, which is 10,000ths its size, which is made up of protons, and that's made up of quarks. And here is a poor depiction of what a proton is. It's basically up, and down quarks tied with something which we whimsically call gluons. Okay? When you can't see these things, this is at distances of 10 to the minus 18 meters. You can call it anything you want. Quark, lepton, gluon. So that's what we do. The standard model, this is a combination of quantum mechanics and relativity. It's a field theory, quantum field theory. I said that to impress you. I'm not going to explain what a quantum field theory is. There isn't enough time for that. But it's a field theory, and that's important. Basic ingredients are fields, including, for example, electric field or magnetic field, as you see here in a bar magnet with iron filings. You see the fields of the magnetic field. So there are fields like this, gravitational field, and then there are other fields. So this theory is based on fields. And it is, in fact, the crowning achievement of the 20th century science. 31 Nobel Prizes, experimental and theoretical, have been given for basically this synthesis, which says nature is made up of quarks, up and down, charm and strange, top and beauty. Physicists have a sense of humor. Leptons, electron, which is familiar to you, a neutrino, and something called the muon, which is very much like an electron, much heavier, and tau, which is also much heavier than the muon. All of nature that you see today could be explained by just these four things and the force carriers which mediate the interaction between them. Gamma for photons, electromagnetic interaction. Gluons, that's what holds up and down quarks together to make the nucleus. The W and Z bosons, which are the source of radioactivity, which is what makes the sun go. But somehow nature has chosen to replicate itself thrice, 3 families of matter. And my earlier research that Mark referred to was to explain why. What was the question when the answer was 3? But we won't go there right now. But you see, there are a whole bunch of quarks and leptons. These guys, the second and third generation, they are sort of extinct. You don't see them in nature anymore. You have to go back. You have to go back to a machine or go back to early in time when things were very hot, and that's when these dinosaurs existed. But they're an essential part of the theory. Looks great. As I said, 31 Nobel Prize. None to me. But there is a problem. there is a very big problem. And the problem is here in this chart, which is may not be very clear to those of you sitting in the back. Here, this is a scale where one can go and measure the masses of each of these subatomic particles, these elementary particles, and just graph them. And you find something utterly bizarre. Neutrinos are here, 10 to the minus 12 electron volts. Electrons are here, charm quark and top quark. As a matter of fact, the electron is 350,000 times lighter than the heaviest quark, which is the top quark. And if you look at this picture, it makes no sense. There is no pattern, there's nothing. It's there. These particles have mass. Photons are massless. Gluons are massless. These are bosons. But there are two other bosons, W and Z, which have the mass about the size of a silver atom. This is all in the Standard Model. This is the beautiful theory for which 31 people got Nobel Prizes. So the question is why? Why do you see this spectrum in masses? And it's an experimental measurement. This is not a conjecture. You can produce these things. E equals mc squared tells you exactly how much energy you have to pump in. You can measure the mass. So this is a massive problem, no pun intended. And here is the problem. Standard Model has no mechanism for these observed masses. Worse, in this theory, all fundamental particles are massless. Now imagine a world made up of quarks and electrons where everything was massless. Well, nucleus would be kind of okay, but I won't go into that. But the electrons, they're massless. They would just fly off. Okay? So when things get massless, things start flying off at the speed of light. And so you have no atoms, no periodic table, no chemistry, no biology, no stars, no us. Well, this is not the universe that we live in. And so the Standard Model, at this point, cannot be a full theory. It's missing something very vital because we exist and flowers exist. So this is about the time UCSD was formed. I mean, this is not a recent observation. People knew about this back in '64. And so we have a massive problem. And here is a one way out, a very elegant way out, which is to add, an elegant but ad hoc way out, which is to add a scalar field, the so-called Higgs field. And here are a bunch of people who contributed to that idea. It's again a field. It's a scalar field, and that has some implications. What that means is that universe is permeated by a Higgs field, and the way particles get mass is by how they interact with this Higgs field. Okay? There are particles like photons which do not interact at all, so they are massless. And then there are particles like W and Z bosons which interact rather vigorously with this omnipotent, omnipresent field, and they have a mass, pretty heavy actually, the mass of a silver atom. Now, how do we know that this isn't just fancy theory, whether it's truly a description of the origin of mass? Okay? We don't know how many Higgs fields there are. But what we do know from quantum mechanics is that if Higgs fields exist, there must be a quantum particle, a ripple in the Higgs field, just like photon is a ripple in the electromagnetic field associated with this Higgs field, and that is the Higgs boson. And it's time to hunt the Higgs boson to really confirm what is science and what is fiction. It has taken us many years because the technology to do these kinds of experiments has only become available recently, and I'm going to devote the rest of the talk not to theory, this went on too long, but to the apparatus, to the accelerator, to the detector, and where we are with respect to the Higgs boson. We need 4 things to find the Higgs boson. You need an accelerator, a machine, for example, that can accelerate protons to very high energy. Here's an example. And then collide them, smash them together. Very, very high energy. You need a detector. You need a camera. At the point where these collisions happen, you want a camera, a very fast camera, which can take pictures of this little baby universe that you made. the amount of data that comes out of these collisions is so much that your laptop isn't enough to analyze it. You need the whole world and computers of the world together to process and store all the data that this is generated. And most importantly, which you can't see here, you need people with special talents which come from every part of the world. It's a collaborative science. There are thousands of people in this, and they all have very special, detailed talents, and they are needed to design, build, and operate these machines. So in the rest of my talk, I'm going to expand on this and then hit Higgs boson and where we are. I can tell you we haven't found it yet, so if you wish, you can leave now. So what do we need particle accelerators for, like the LHC? Well, for three reasons. If you accelerate particles to extremely high energy, de Broglie's principle tells you that if you want to look at deeply into nature, like if you want a powerful microscope, then the resolving power depends on the energy with which you are probing. So when you have a high energy particle, you're probing very small distances smaller than 10 to the minus 18 meters per second. E equals mc squared also says that if you want to discover new massive particles, you got to have the juice. You got to have the energy. And that's why you need these particle accelerators. And third, if you want to study the young universe, there is Boltzmann's equation, which tells you that energy is related to temperature. So when you produce collisions of very high energy, you are recreating situations where the temperature was very large. So you can go back and turn your accelerator into a powerful telescope which looks back in time when the temperatures were very, very large. That's why you need a particle accelerator. But we want to do it all in a controlled way, in a laboratory, okay? In a way where I can turn on the ignition and things start firing. How do you build a particle accelerator? Well, you start with something like a hydrogen gas cylinder. Then you get some accelerated material like a battery. You know, if you had like 7 billion of these stretching from sun to earth, that would be very much like this machine that I'm going to talk to you about. But you need a source of juice which can take electrons and protons and propel them with higher energy. They need a magnet. You don't want these guys to go out of control. You want to bend them around such that they move in circles. Or you can make them do whatever you want, change the magnetic field. And that's the equation. Okay? Now, turns out, I'm betting here, that almost all of you, above 30, owned a small particle accelerator at home before you traded it for one of those super giant LCD TVs, maybe plasma. You know, it used to look like that, you know, a cathode ray tube basically. You had an accelerator. All you needed was to connect it to a power source of about 7 billion volts, and you would have an accelerator. LHC is that accelerator. Protons are accelerated by powerful electric fields and then guided around in a circular orbit by superconducting dipole magnets. These magnets, because of the energy of the protons, are very, very strong, 8 Tesla, about 200,000 times the Earth's magnetic field. And to build such dipole magnets, you need superfluid helium and lots of it. And so protons travel in a tube which has to be kept under better vacuum and under lower temperature than outer space. All this, as you will see, 100 meters below ground. How do you feed it? Well, surfing. Surfing is a good example. You take a proton and you put it in front of an electric field, and the proton is just happy, you know, just like the surfer here in a wave. And so here is the surf is up. That's when the proton goes through. That's how you feed it energy. And you need to do that because you start off with protons not moving very fast, and then very soon you have to get them going, in this case, at a speed just 3 meters per second less than the speed of light. That's how fast you want these things to go. I'm going to skip this. So here is a real dipole. This is the bending magnet which keeps the proton going, and here is the is a landscape. These are the Swiss Alps on this side, there's the Jura Mountain on this side, Lake Geneva, and 100 to 185 meters below ground is this tunnel, complex of tunnels, where this is the LHC machine, and I'll show you a little visual of that. You see every bit of this 27-kilometer circumference machine collider had to be built piece by piece by lowering things like this dipole weighing 18 tons, thousands of them, down the tunnel to make this little circle. Let me show you a video of how this works. So you start with a hydrogen. So here is your hydrogen atom accumulating here in some chamber. Now I'm going to apply an electric field and strip off all the electrons. So what I'm left with is just a proton. I'm going to squeeze them together nicely so they form a nice bunch, and then enter it through a LINAC, nothing but a big battery. These are protons, they're going towards the negative, and at this point they are at velocity 1/3 the speed of light. Now they go into a chain of rings. Okay, the first one is going to accelerate them by giving them this radio frequency electrical field, and then these particles are kept in the orbit by the magnets. Okay, not very energetic magnets, but magnets, and then they keep going round and round, and you can keep feeding it energy like a horse in a racetrack with a carrot in front of it. And then this goes on for a while. There's a whole chain of accelerators which increase the energy of these protons. There are many bunches of protons now being put in, and now the protons are traveling very close to the speed of light. But this is not enough. We need more. More of the proton, more of the energy. So you push it in to what is called SPP bar S. And here, this is, as you can see, these things are getting bigger. And now we have billions of protons in one bunch. And now it enters the Lord of the Ring, the LHC. And this is where it is. This is the sort of zoom out of this region near the Jura Mountains. And here it is. Now we take protons in these two pipes and counter-rotating beams of proton. For example, one goes this way, the other goes this way. And so now you have protons circulating in opposite direction, and the intention is to bring them together and smash them. Now we have a particle accelerator. And this is the place where, using deflectors, we can in a controlled way bring the proton and proton head on, smash them together. So at this point in the LHC, the velocity you just saw was 3 meters per second, just less than the speed of light. And here are the protons with quarks and gluons in them now just zooming through this beam pipe. And you know what's going to happen? They're just going to come together very soon into a camera, the detector, and that's where the collision is going to be. And that's the picture we'll take. And that's how we'll find the Higgs boson. So the next step, that was the accelerator. Now the detector, what we need is a camera, a fast camera, a little bit faster than, this is not a bad camera, it's a D90, but we need something faster. So the camera has to sit where these collisions happen, right? Okay, the collisions have to happen right at the center of this camera. And this camera is or detector is a concentric layers of sophisticated cameras, which are sensitive to different kinds of particles and respond to them in a very characteristic fashion. The idea of this camera is to identify and precisely measure all the energies and all the directions of the particles which are produced when these proton-proton collide. You saw the energy which flew out when in the sim animation when the two protons collided. So that's what we want to do. And here is the camera. It's kind of heavy, 12,000 tons. It's kind of big, 15 meters in diameter, and it's 21 meters long. To give you a sense of the size, you certainly don't see it here, but this is the size of a human being. There is actually a human being here, okay? And it's got, as you can see, concentric layers of different detectors inside a magnetic field, and this is sort of an exploded view. It's actually pretty compact, okay? As compact as 22-meter long things can be. That was a rendition. This is the real thing. There is a 100 million pixel camera, the real thing. It takes picture, as I said, a little bit faster than your digital camera. How about 40 million times per second? That's what it has to do. Okay? Now, I'm just going to show you some pictures. I mean, these things are not made in one day, and you just don't go out to Radio Shack and buy it. I mean, you have to develop all these things yourself, and that has taken. This is why when people say, why does it need 2,000 people? You get a sense of the scale of what has to be developed, okay, and the expertise that is needed. So here again is the overall view of the LHC. This is again the Swiss Alps. This is the underground. This is CMS, like there. And here is the region, a blow up of that area. There are all kinds of shafts. And here is everything will basically drop down, or materials and supplies, or air conditioning and power, all these things will come out from here. And here it was at construction time. This is at the surface. The detector that I'll show you was mostly assembled here. And you see a big hole here. And it is through this hole that these tons of detectors weighing tons of kilograms will be dropped down in a one-way fashion. Show you some pictures. This is pretty scary. So this is that hole now, the shaft. And this is the area being cleaned up. There was a lot of water when this thing was coming up. So the whole, every bit of the detector, that giant thing that you saw, is over the years coming down through that shaft. I'm just going to show you these things quickly. One by one, they all come down, okay? And it's gravity which is putting them down. There's no way, if one messes up a little bit, there's no correction. There's no tolerance. You can't go up, you can only go down. Sort of like Hotel California. One of the huge discs, I mean, I have seen these pictures a lot of times, but I'm still amazed at what it took and the engineering that it took to bring all these things down without anybody being killed, without any damage, okay? It's a remarkable engineering feat, the whole thing. Here is a magnet. It's a 4 Tesla magnet, and things are kind of wrapped around it, different detectors. There's a lot of plumbing to conduct heat away. There's a lot of wires. There's a lot of electronics, some of which sits on the detector, and the others get pulled out up in the surface area. This is my favorite. This is one of the most sensitive elements of the CMS detector. It's 200 square meters of silicon strip sensors. Okay, not unlike things that go into your camera. 200 square meters. Okay, that's a good swimming pool. So now it goes in, and finally we are ready to close. Here is the beam pipe. This is how the protons are going to come in. Everything is nicely wrapped up, and we are done. And this was the situation a few years ago. I want to make one quick story whose title is War to Peace. You see, when we built this giant thing, there were all kinds of materials, very specialized materials that were needed. This is extreme science and extreme engineering. One of the things that was needed was brass, very high purity brass, and with mechanical properties which you could not find in the world, at least not cheaply. We are cheap. But we had some Russian friends, Others have Italian friends, we have Russian friends. And they said, well, I seem to recall that in the that there are some ships with all these shells, brass outer shells, with ammunition inside them, which the Russians sort of had stockpiled during the Second World War and a little bit later. And they're probably not using it anymore. So why don't we go ask? So we asked the Russian government, could you please give us these shells? And they said, okay. And they even agreed to remove all the explosives. So you see a bunch of people, they're kind of not terribly happy, but they don't look scared. And that's because all the ammo is gone. And then the job is to take all this weapon of war and turn it into plates of brass, which is what this guy has been doing. It's been a long day for him. You can see he needs at least 1 beer, maybe 6, okay? And that's all the brass plates. And then finally, you put it all together, and that's where it is, a piece of science from a weapon of war. So that's CMS. There's a similar picture for Atlas, but I'll just tell you that this is the competition. It's pretty good, and it's bigger than us. But that doesn't mean they're better than us, okay? This is the scale of things. You know, this object is the size of a modern cathedral, okay? This is a 6-story building at CERN. Atlas is taller than that, and CMS, which is a compact muon selenide, is only half as big, okay? But one thing you have to appreciate, that big that they may be, these are super precise machines. They're more precise. The data that comes out of them is much more precise than the accuracy of a Swiss watch, for example, or a Japanese watch. So these are very precise instruments. So now I've talked to you about an accelerator. I've shown you a camera. Let's put the two together, because what comes out of it is what we will examine when it comes to searching for the Higgs boson. And so I'm going to show you another video. Do you like video? Okay, so we'll pick it up with the accelerator. This is a bunch of protons. You saw this earlier, going through, picking up speed, going faster and faster the speed of light. And you know, the whole, I'm just showing one bunch, but there's several bunches. Here they go into LHC. And now I'm going to show you a proton eye view. So it's going through here. You see there's some graffiti here, and you know, some nerdy physics stuff. The protons go through Switzerland, France, no visa required. Here they are, dingling away, not knowing that there's a proton on the other side. And they're both going to meet right here in the center of this camera. And here they go. They don't know each other. Good morning. And that's the energy that is released from these collisions. And it's catching this energy, the direction in which this energy flew, what particles there were. This is what a camera does. That's what the detector do. And at this point, by marrying this collision with this camera, now I know exactly what happened when this collision happened. And that's important if you want to find new particles like the Higgs. So here are some snapshots of pictures taken, real pictures of protons coming in this side, and this is from our competition experiment. And just to tell you how broad-minded I am, I'm showing pictures from my competition. And so here is an interesting event where a muon passes through, and it's pictures like that I'm going to show you a little bit more of. Here is another one. If we had found this in 1984, you'd have got a Nobel Prize. It's the Z boson. It has got 2 muons going through, and you can see that this is the picture of the 2 protons colliding, some of the debris and some heavy stuff indicating that the collision was close to head-on. Now, computing. The detector is a 100 megapixel camera. It takes 40 million pictures per second. And so the first thing to do is to select which pictures are interesting. So let's just pick like 100,000 per second. Each one of them was 1 megabyte. And then you send it to 50,000 CPUs to see, tell me, which of these is interesting? Because in the end, you only want to keep like 200 or 300 pictures. And even if you just did that, this generates 10 million gigabytes of data per year, which is 3 million DVDs per year, which has to be stored somewhere, analyzed, and the conclusions reached in your lifetime, or hopefully in a year or less. And so what you need is extreme computing, and that's what the computing grid is. It ties up computers and the storage from all over the world. Here is a depiction of this tie-up. For example, it reaches 34 countries, 100,000 computers, and they all work synchronously together. One of the experts in this kind of development is Frank Werthwein, who is a professor here. And we have one of these centers right in Mayer Hall, not far from here. So computing, people. This is the map of the world. And the ones in red are the countries and regions which are part of just this CMS detector. There are 2 detectors. Atlas is the other one of them. And so we have about 2,500 scientists from 130 universities from 38 countries. And trying to herd them together is like herding cats. It's not so easy. So physicists don't necessarily like to listen to other physicists. But it's a truly global collaboration. People work together because they have common interests. For example, like finding the Higgs boson. US is a very strong part of the LHC. There are 1,700 scientists. This is the distribution of these. And as I said, UCSD is one of the premier institutions in the CMS experiment. So now we have everything. Next step is to start looking, start finding. 2010, this was the year when we started. This was our commissioning year. You know, it's like buying a new car. You want to take it for a test spin. You don't want to completely, hit the gas. So in 2010, what we did was just commission different parts of the detector, the computers, the machine, and everything. And this was a spectacular success for the machine. We started on 30th of March, and this is the rate at which we recorded data between then and November. And you can see, we spent some time trying to understand the machine, and then slowly, this just went off the charts. If my stock portfolio in 2010 had been like this, I would probably not be giving this talk. There was enough data. This is not too much data, but there is enough data that now we can see what we should have seen, what people saw, in a century of experimentation. And so this is a spectrum which has this continuous shape, but it also has these little peaks, these little spikes. You know what these are? Each one of them is a Nobel Prize winning discovery of the 20th century. This is how the Standard Model was made. These are some of the 31 people who got the Nobel Prize for the Standard Model. And we rediscovered it within first few months of running. That's the power of the LHC. What this also tells us that we know exactly what we are doing. The fact that these peaks show up where they should, because they have been discovered at those masses, says that the next step, which is to look at masses much larger than the mass of a silver atom, if something is there, we will be able to find it. So it's a very good validation of our capability. Okay? Not just of CMS, but also of ATLAS. And without it, we would, if we didn't find Higgs, how did you know you were capable of finding it? Well, this is proof. You should now find it. So we did find Higgs, actually. And we found him even before the LHC started. It was a miracle. In fact, it was Peter, Mr. Peter Higgs. So he came and he was very curious, and he wanted to make sure we are not going to screw up, not find his particle. So that brings us to the Higgs itself, setting the trap. Well, a large part of the trap has already been set. The machine is built, running beautifully. The detectors are performing very well. Computing is in place. The people are there. Now we just need a game plan to look now and to follow in the next 2 years. Okay? So this is how we form that game plan. What do we know about the Higgs? We know that it's very rarely produced. I won't tell you anything about this. This is just to tell you I know what I'm talking about. Okay? It's very rarely produced, even in proton-proton collisions. It disintegrates immediately after its birth, just breaks up into a whole bunch of different other subatomic particles. What we need to do, as I showed you when we talked about the detectors, we need to pick up all the pieces that the Higgs boson decayed into to go back and reconstruct what was this object, the mass, the nature of this object. But what it disintegrates to depends on what its mass is. Here is the problem. We have no idea what its mass is. At least the theory I told you has no idea of what its mass is. So what do we poor experimentalists have to do? Sleep less and look everywhere and do it efficiently. So depending on how heavy the Higgs is, it will have characteristic signatures which our cameras are equipped and set to catch. Now I'll show you some pictures. These are simulations. But before I do that, question is, you don't know what the mass is. There have been people before us. They have also wanted to search for the Higgs. And here I show you the landscape, the lay of the land. The Higgs could be anywhere here. This is the experiment that I was at before I came here, an Aleph experiment, and there are 3 others like that. And we searched for the Higgs all the way from mass of 0, and then we ran out of juice at 114 billion electron volts, okay? Which is about a little over silver atom. Tevatron, which has been running recently and done a valiant job, has also ruled out a tiny sliver. So this is where it's red, that's where the Higgs can't be. But you see that there is a whole landscape that remains to be probed and conquered. And this is what we are going to do. And so we have a game plan for different parts of this mass region. One of the experts in a very special form of Higgs disintegration, when Higgs decays into 2 very energetic photons, is Professor Branson, who's sitting over there. And here is the kind of a picture. This is an analysis that he did some time ago, making the strategy of how he would find the Higgs. And what you don't see here, you don't see the Higgs because it decayed, and it decayed into 1 photon which went this way and the other photon that went this way. This is how you would find it. This would be a signature. This would be an interesting candidate for you. But Higgs can also decay into other things. It likes to decay into heavy stuff, which then decay into other stuff. And here is another possible scenario in which the Higgs could be. These are all traps. The detector is programmed, analysis chain is programmed, that any time something like this pops up, it gets sucked out. And as a matter of fact, one of my postdocs, when we were beginning to look at the first data, we had set it up, if an interesting event came by, it would ring my mobile phone. The computer would call my mobile, and it did at 4 o'clock in the morning. Okay, so we are kind of know how this is done. How will you know you have found the Higgs boson? Well, you will take these interesting events and catalog them, put them up together, plot the mass. Remember, you reconstructed all the things that the Higgs decayed into. Now you just plot the mass. And if you see a spike like this, an excess like this over what is expected background, you got it. That's the Higgs. Question is, what mass will the spike show up, and how much background there will be? So that's how you will know that you have found the Higgs. And you can see that the excess is pretty statistically significant. And that's, when you are looking for the Higgs, you want to be sure. And the standard of proof is that you have to be sure that you haven't made a mistake at least 1 part in, hopefully, a million or a billion. Billion is better, okay? But that means you have to work harder. Then a beautiful thing happened, okay? A beautiful event walked into our detector. And unfortunately, the lighting is not very good, so I'm going to skip it. But here is what it looks like. It is this is a picture of a sort of a 2D picture, a cross-section of the detector. And what you see here was, this is where the collision happened. Some particle was formed here, and it zipped out. It decayed into 4 muons, very energetic. This is an extremely beautiful event. Very easy to analyze, very easy to understand. And it has the topology of what a Higgs would look like. As a matter of fact, it could well be that this is a Higgs event, okay? And if it were, its mass would be 200 GeV, okay? A little bit more than gold. But this is the only event, only interesting event we have. And it's just as one swallow doesn't make the summer, one event does not make the discovery, because as I said, nothing is super clean. There is always background. And you have to estimate when you're trying to say, what is the probability that what I have seen is the Higgs? You have to ask yourself also the question, what is the probability that I have seen garbage? Okay? And it's only when you rise over this probability and significance that you say that I have found the Higgs. So one event is too few, but it does encourage us. You know, this is, as I said, 2010 was not the year where we should have found the Higgs, and we in fact did not. Okay? But the beauty of events like that and the way we recorded them tells you that the camera and the machine are working beautifully, that they are ready. And we're just waiting. If this is Higgs, there will be many more like this which will walk into the trap that we have set for them. So what's happening now? 2010 is gone. This is what we got. The immediate future, well, in 1 year, in the commissioning year, we improved the performance of LHC by a factor of 100,000, which is not bad. Okay? But we think we can do much more than that. As a matter of fact, the more we improve the performance of this machine, the faster we get to the sensitivity for the Higgs boson. So people are very motivated to improve the performance by even a factor of 20 or 50, depending on their level of enthusiasm and competence. So what's going to happen? There is a meeting happening right now. The decision will be taken tomorrow, but it's kind of like a done deal. In an international organization like CERN, you have to go through a whole process before you decide. But we know that this is going to happen. So far, we are running at half the LHC real energy, but now we'll increase it from 7 TeV to 8 TeV and accumulate at least 20 to 100 times more starting this spring. And the main reason for this aggressive performance plan is the Higgs search, that we want that in the next 2 years, we close this chapter of discovery. So we make plans, we make projections. We know how the detector has performed so far, how much data do we need, how much well do we understand the background. And on basis of all that, we make a plot like this. This is one of my last plots, and it's kind of complicated, so I want to take a couple of minutes, because in the end, this is the most significant thing. This tells you what we can do or not. So what is shown here on the x-axis is the mass of the Higgs boson. We don't know what it is, so we have to look everywhere. And what is shown here is that at the end of the day, after setting the traps, after making sure that the backgrounds do not pollute what would be a Higgs signal sample, this is the significance of observation, okay? Which is a way of saying how significant, how statistically significant, when I say that I have found the Higgs, how sure am I? And I told you about close to 1 part in million. That would correspond to a number 5 here. And you can see that in the scenario that we are looking at, 8 TeV, 2 to 5 inverse femtobarn, we are almost everywhere above 5 sigma. Okay? And so basically, until a mass of 600 GeV, if the Higgs exists, if the Higgs doesn't exist, well, you know, I tried. But if Higgs exists, this picture says that it will come. Okay? So we wait. In a couple of days, I go back to Geneva, which is where I'm stationed, and start exercising for the run which is coming up in March, because this is going to be relentless for the next 2 years. Okay? And so will my colleagues. There'll be some of them are teachings. They'll be traveling back and forth. And so this is going to be a lot of fun. So I think this is all I have to say in the story of mass. This is my story. I'm sticking to it. And I just want to tell you as a summary that, that just last year, this is a Da Vinci style painting, a window into the unknown. And LHC opens this powerful window in search of the Higgs boson, or whatever it is that causes the origin of mass. And next 2 years is when we hope to make substantial progress in that knowledge. Thank you, and stay tuned. The question was, it's a general purpose apparatus, as I said, so do you have to share with people? And the answer is, our mode, the way high energy physics works, is that we build the apparatus together. So even if you are interested in measuring, finding about supersymmetry or finding Higgs or extra dimensions, you all come together, you build the machines together, the infrastructure together, and it's the same collisions which are shared by everybody. So there's no special time as in astronomy for particle physicists. We share everything, and we share with everybody. And it doesn't matter if you paid $50 billion more than the other guy, you get no extra privileges for that. Everybody, it's a meritocracy, but it's a democracy. Yes, sir. Yeah, so there are two, as I said, there are actually 4 detectors, but there are 2 detectors which are called CMS, which is the one that all of us from UCSD work on, and the other is called Atlas. I actually showed lots of event pictures from Atlas and even showed the images of that. Both of these detectors, now when you're trying to discover something new, it can't be done by one. You always want a cross-check. And the cross-check has to be as good as the original. So you build a pair of detectors which have the same capability. So if CMS finds the Higgs with similar amount of data, Atlas, which is sitting at the other end of the ring and collecting data in the same Fourier space, they should be able to confirm our observation. So from the very beginning, there were 2 detectors which were designed, constructed to be equal in performance. And the data of last year has shown that this is in fact true. And that's a beautiful thing, because now we know that, if we find something, we would like a confirmation. If we don't want something, I'll sleep better if somebody else tells me they didn't find it either. So they're both doing beautifully. As a matter of fact, I should say, LHC, CMS, and Atlas, the start that we have seen has been unprecedented in the history of science.